Hello and welcome to NPTEL online certification course on aero engine gas turbine cycles. Today it's lecture 9. So, what all we were discussing in last lecture was the component called compressor. We were discussing about the construction detail of compressor. Then we were discussing about the compression process on TS diagram. We tried to analyze the compressor using control volume approach because that is what is of our need for fundamental understanding. Then we started discussing, we tried to criticize the compressor using the performance parameter like isentropic efficiency and polytropic efficiency. So, we end up with one numerical. So, let us start solving that numerical and then we will go with the next component. So, in last lecture we have seen we were given with this numerical. It says the compressors of gas turbine engine that has total pressure ratio of 10 and 16. We need to calculate the adiabatic efficiency if the polytropic efficiencies are say 90% and 92%. So, this is what is a given data and we want to calculate our adiabatic efficiency. So, let us start with the first case. What it says, we are given with the information, say my compression ratio is 10 and polytropic efficiency is say 90%. So, what we know, our compressor efficiency, that is what is given in terms of pressure ratio and in terms of polytropic efficiency. With the given data, let us put these numbers. It says if we are using compression ratio of 10 and polytropic efficiency 90%, we are getting our efficiency as 86.4%. So, here on right hand side you can say the x axis, that is what is representing my compression pressure ratio and y axis it is representing my adiabatic efficiency. Say my second case, it says if I am changing my polytropic efficiency to say 92%, what will be the change in my say adiabatic efficiency. So, here if I will be putting this as a number, it says I am getting my efficiency as 89%. So, here this is what is representing my efficiency as 89%. Now, one more information, it says if I am having my pressure ratio of 16 and my polytropic efficiencies as a 90% and 92%, what will be my adiabatic efficiency? So, let us calculate that part. If I will be taking my compression ratio to be 16 and polytropic efficiency as 90%, it says my adiabatic efficiency is coming 85.6%. Same way, if I am taking my polytropic efficiency as a 92%, I am getting my adiabatic efficiency to be 88.5%. So, there is a reason behind doing this calculation. So, let us try to analyze what is the meaning of this information. Suppose say if I am increasing my pressure ratio again to say 22, maybe 25, 28, with the change of my polytropic efficiency, my adiabatic efficiency, that is what is changing. So, it will be changing like this. Now, this is giving lot of information, that is what we need to understand, we need to realize. Let me put the point here, what we say is polytropic efficiency. This polytropic efficiency is per stage efficiency. Suppose if I consider I am having say 10 stages, for each stage I can assume my polytropic efficiency to be say 90% or 92%. Based on my pressure ratio, accordingly my adiabatic efficiency, that is what is varying. So, what is the use of this? So, when we are doing our cycle analysis, we need to assume the efficiency. That efficiency we say polytropic efficiency we are assuming, and this polytropic efficiency we will try to maintain to be constant during the off design condition also. So roughly it says this polytropic efficiency can be assumed in the range of 88% to 92%. Now let's try to analyze this part. What we know about compressor? It says compressor is working under adverse pressure gradient. And if I consider say per stage pressure rise to be higher, what is the meaning of that? Suppose say if I am looking for pressure ratio of 10, I can go with 8 number of stages, 9 number of stages, even I can plan for say 4 number of stages, but that 4 number of stages, that is what may not be possible. The reason here is per stage pressure rise, if I will be using to be higher, then I have the problem in terms of my efficiency in my operating range and the performance. So that is what is because of my adverse pressure gradient. So it says we will try to put additional stages. If I will be putting my additional stages to avoid the flow separation problem and in order to improve my efficiency, then we have other kind of issue. The issue here is, since the compressor is power consuming device, so my power requirement will be higher. So like more compressor stage, that is what people they are defining that as a burden. So here in this case, if we consider for the pressure ratio of 10, I can go with say more number of stages with say a higher polytropic efficiency, or maybe I will be going with say less number of stages with the other polytropic efficiency, but at the same time I need to compromise somewhere in terms of my adiabatic efficiency. Suppose if I consider I am increasing my pressure ratio of 16, if I am increasing my pressure ratio of 28, you can understand for the similar polytropic efficiency range, we are having our adiabatic efficiency, that is what is decreasing. This is what is very important. When we will be discussing about the cycle analysis, you will realize this point and you will you will try to appreciate the part saying like, oh okay, this is what is important to be analyzed before going into the detailed cycle analysis. So here we understand the part saying like polytropic efficiency and our adiabatic efficiency, and you must realize increasing the more number of stages, that is what is demanding for additional thing. When we will be discussing about the turbine, you will get surprised with what all we will be getting. We will discuss this part again during the discussion for the turbine. Now let us move towards the next. Say this is what we were discussing about the single stage turbojet engine, and now we are focusing with our next component, that is what is combustion chamber. So this combustion chamber, if you look at, that is stationary device which is connecting my axial flow compressor with the axial flow turbine, and this component it is of great use. Now let us try to look at what is the use of that. So again here it is representing this Pratt & Whitney high bypass ratio engine, where we are having this high pressure compressor, that is what will be connected with my high pressure turbine using this combustion chamber. Same way here, if you look at, this is also combustion chamber, but if you look at in terms of construction, that is what is different. Here my flow in centrifugal compressor, it is entering axially and it will be leaving radially. Here in this case, my flow in compressor is entering axially and leaving also axially. Okay. So now in order to have my flow to be entering axially in axial flow turbine, I need to design my combustion chamber that is of different shape, and this is what is called reverse flow annular combustion chamber. Okay. Now what is the size of my combustion chamber? That is also equally important, because we can say I have the restriction with the length of the engine. So I cannot put say bigger size combustor in order to achieve the few requirements. Okay. let us see what all are the important parameters here. So, here this is what is representing the combustion intensities for different kind of heat engines and their combustion process, say for boiler furnace, for piston engine, for jet engine, for rocket engine. So, we are at this moment discussing about the jet engine. You can say the combustion intensity, that is what will be in the terms of say 21 to 42 into 10 to the power 2 to the 10 to the power 3 kilowatt per meter cube. So, you can say that is what is very high intensity per meter cube volume. Okay. So, here if you will try to compare, you will realize for rocket engine and for jet engine, my per volume heating capacity, heating intensity, that is what is very high. Now, what all are the requirement for the combustor? So, very first we say it is used to raise the temperature of air to the highest level as per the requirement for my cycle. So, we must understand the maximum cycle temperature, that is nothing but it is exit from my combustion chamber. Now, this is what is with the specific reason, higher will be my turbine entry temperature, higher will be the work extraction we will be getting, and we will see that is what is giving the higher efficiency of my engine. So, the higher temperature, higher work extraction, that is what need to be fulfilled with the combustor. It says we need to have minimum loss in the pressure. At the same time, hot gases that will be delivered at uniform pressure and temperature with the limitation of my turbine blade material. At the same time, we need to do our acceleration and deceleration of the engine. Accordingly, we need to give the variation in terms of flow rate coming out from the combustor. It should be having say ignition that to be rapid, reliable and sustainable. It should occupy the less space and it should burn with the range of my fuels. So, these all are the requirements, that is what is been targeted by the engine manufacturing company, engine design companies. So, let us try to understand what all is a combustion process. So, here if we will try to look at, it says in order to have our combustion, we need to have high pressure and high temperature air. And if you recall, the exhaust that is coming from my compressor, it is having high pressure and high temperature air. This high pressure and high temperature air that will be entering inside the combustion chamber, where the fuel, that is what will be sprayed. So, very first thing or the step, it says the spray through the injector. Next, it will subject it to atomization. Because of the temperature rise, we will be having evaporation, proper mixing of my fuel and air. Then we will be having ignition. Because of this ignition, we will be having the heat release and the mixing of this combustion product. After all, this will be delivered to the turbine at required temperature and the pressure. So, here this is what is a very good representation what is happening in our combustion chamber. So, it says we are having air supply and liquid fuel supply. Remember, here I say liquid fuel, people they have started using gas also. There are a lot of trials which are going on for using hydrogen as a working fluid, hydrogen gas. So, future engines may be having hydrogen as a working fluid. So, here in this case, this will be injected of the fuel, and that is what will be subjected to atomization. When we say atomization, it will be having evaporation and droplet formation. These two will together, it will be increasing the turbulent intensity inside, it will be giving the proper mixing, and that is what will be giving the gaseous phase reaction and droplet burning. And after doing all this, it will be giving the reaction product, and this reaction product we say it is a combustible gas, that is what will be coming out, and this gas, that is what will be supplied to our turbine. So, it need to perform lot of operation within my combustion chamber. Okay. Now, this is a structural diagram. If you look at the combustion chamber, from entry I am having the air, that is what will be entering inside the combustion chamber. Now, initial phase, we can say, in order to have the combustion to take place properly in a systematic way, you need to have your air velocity to be lower. So, initial part you will be having the diffuser, that is what will be diffusing the flow. So, at the entry of the combustor, this Mach number will be in the range of 0.25 to 0.35. Here the air, that is what will be passing through this particular region. Here we are having the swirler and the fuel injector, from where the fuel will be injected, and this initial range, that is what is called primary zone. Next zone, that is what is called intermediate zone, and the next zone, that is what is called dilution zone. So, it says almost 20% of my air, that is what is been supplied in the primary zone. Then later on the remaining portion, that is what will be supplied in the dilution zone. So, the intermediate zone, that is what is very important, because with a change of altitude my pressure requirement, that is what will be different. We say at low altitude operation the high pressure in the combustor, that is what is happening, and here it may subjected to say poor mixing. At the same time, for the high altitude where we will be having say lower pressure, under that condition my reaction, that is what will be going say slower. After this, here if it is passing through the intermediate zone, so from this primary holes, that is what will be subjected to have the cooling air that is passing through it. Since the combustion, that is what is happening inside my combustion chamber, this wall will be raised with the temperature. So, it need to be cool. So, different kind of cooling mechanism they are being used for this purpose. Later part, if we go through, it says the dilution zone, where we will be having dilution of air or mixing of air and the combustible gas, that is what is happening. Here this is what is maintaining my temperature, that is what we will be supplying to our turbine. Okay. There are different types of combustor what we are using. It is called single can kind of combustor. So, here this is what is representing single can. It is also defined as a reversible flow combustor. So, from here the flow, that is what will be entering inside my combustor. Somewhere here I will be having the fluid injection, that is happening primary zone, secondary zone, dilution zone, and from here my gas, that is what will be discharged to say turbine. Same way people they have organized this can in a different way. It says tubular or multiple combustion chamber, where we are having different cans, they are interconnected. It is called tubular arrangement. So, this is where I will be having the center portion, that is what will subjected to my shaft placement, and here this is what is been connected with the interconnector. Now, we will be having say other kind of configuration, where we will be having turbo-annular kind of configuration, or this is representing my different can, different combustor, they are being placed in a systematic way. This is a different kind of configuration, where we will not be having this can kind of configuration. Here let me put the point, this when we are using say can type or say tubular kind of configuration, where we are having the flexibility that the flow through this combustor, it is in control, where we will be having very good mechanism for cooling, but at the same time my combustion efficiency, that is what will be going lower. So, recent trend it is to use of annular combustor, where you will be having say multiple fuel injector, they are being placed in systematic way, and the same way we will be having the placement of primary zone, say secondary zone and the dilution zone, and the exit from that, that is what will be entering inside the turbine. Now, let us try to analyze this with the control volume analysis. So, here I am considering this as a burner, and for this burner I am putting this as a control volume. Let us try to analyze here. In this case we are having compressed air which is coming out from the compressor that will be entered inside my combustor or the burner. We are injecting the fuel here. At the same time, the mass flow rate which is coming out from the exit, that is nothing but the summation of what air and fuel we are putting. Here in this case, we can say this is what is representing my cross of boundary for work and heat. So, let us try to analyze what it says. For ideal condition, we can assume this M3 dot and M4 dot, they both are same. If we are considering say my air fuel ratio, that is what is say smaller. Here in this case, there is a chemical reaction, that is what is happening because of combustion, and that is the reason why my Q is not constant or it is not 0. So, it says my Q is greater. That is what is representing exothermic process. There is no work mechanism, that is what is happening, and which is not crossing the control volume boundary. So, we can say our fundamental equation, my Q equal to delta E minus W, that is what is per mass flow basis. Here my W, that is what is 0. So, we can say the change in Bernoulli total enthalpy is equal to heat released during the combustion process. Okay. Now, let us try to analyze this part. Suppose if I consider I want to use my combustor, this combustor also is defined in terms of efficiency. What it says, because of volume limitation, we have discussed within constrained volume we are looking for the combustion to happen, and that is what will be giving what all we are looking for the downstream component say my turbine. So, it says my efficiency of the combustor or my burner efficiency, it is QR actual divided by QR ideal. So, it says the efficiency of this combustor, that is what is highest in the range of 98% to 99%. So, let us put this as a control volume part. It says this is my combustor. Okay. So, M infinity, that is nothing but my air flow rate, this MF, it is my fuel flow rate, and if I will be considering this is what is coming as a gas, I say M infinity plus MF. And if I consider the enthalpy at the entry is say H03, here this is QR, which is representing the lower calorific value of the fuel, this is representing my efficiency, and at the exit I say I will be having the rise of temperature T04, I say that is what is say higher enthalpy, it is H04. So, let me put the balance here. I will say my mass balance, that is what is given by M infinity plus MF, it is M infinity into 1 plus F. This F is nothing but it is defined as a fuel air ratio. Okay. Now, let me put the energy balance. So, what is going inside is M infinity into H03 plus this MF QR into my burner efficiency, that is what is equal to M infinity plus MF into H04. Okay. This we can represent in terms of 1 plus F. So, here in this case this combustion process we are assuming it is happening at constant pressure. Sometimes people they are defining that as a constant pressure heat addition process. This cycle also sometimes people they are defining as a constant pressure cycle. Okay. So, here in this case it says if we are considering the ideal combustor where we will be having our entry pressure and exit pressure to the combustor, that is what will be same. So, my pressure ratio that is what will be 1. But in actual condition what is happening, because of friction, because of turbulent mixing, chemical reaction at finite Mach number, I will be having my exit pressure to be lower than that of my entry pressure. So, it says like there are many reasons for this total pressure to be lost. It says it is due to the incomplete combustion, chemical composition of the fuel, physical properties, thermal losses because of conduction and radiation, pressure losses because of screen friction, maybe pressure drag, all this together that is what will be making my combustor ideal combustor and real combustor to be different. So, it says Kerabrock, he has defined this pressure ratio or the loss, that is what is happening in the combustor, that is a function of my Mach number inside the combustor, and that is what is he is defined as a dynamic pressure. Okay. Now, let us try to look at that on our TS diagram. Here if you look at, this is what is representing my ideal process, where my flow, it is entering at temperature T03. I am adding my fuel here, and because of this addition of the fuel, because of constant pressure combustion, my temperature, that is what will be raised. My raise of temperature, I can say that is what is T04. Now, as we have discussed, in actual condition, what we have, there is a drop of pressure, and this drop of pressure, that is what will give you the exit pressure as say P04. Okay. Here it is very interesting, you need to check my burner exit temperature, that is what will remain same even though we are having the loss of pressure. So, here if you look at, this is what is representing my actual condition and your ideal condition, and these lines which are representing the isobar line. Okay. And here this is what is my temperature limit. Now, let me put the point here. The question may arise in mind, say, we will be adding more amount of fuel, let more burning to happen, it will be generating higher temperature, and that is what will lead to increase my entry temperature for the turbine. But we have limitation. This limitation is my temperature, that is what is entering inside my turbine. Because my turbine blades are having say limitation in terms of metallurgy, it may get melt when it is subjected to very high temperature, and that is the reason why very high temperature, that is what is not been preferred. Okay. So, this is what is putting limit. So, you can say this T04, that is what is deciding how much amount of fuel I need to add with. Okay. So, here this energy balance, it says I am having H04 minus H03. This H03 condition, that is what is been decided with my compressor exit condition, and H04, that is what is fixed with my turbine entry temperature. And here in this case, this is what is defined as MF into CV. This MF into CV is my mass flow rate of the fuel into calorific value of the fuel. Okay. Now, let us see what all are the requirement, that is what is been set by aircraft and engine. So, what it says, we need to have this fuel to be available at low cost and high availability, low fire risk. So, the thing is, what properties we have, it should be low vapor pressure, low volatility, high flash point, higher conductivity, that is what will be minimizing the built up of static energy during the fueling. So, this is what is very problematic case and a serious issue when you are refueling your aircraft. Okay. And this static energy, that is what will be giving you the serious accident. So, now onwards when you will be going to airport, and if you look at people, they are giving the fuel or they are adding the fuel to aircraft, they are taking care of so many things. Okay. Now, next it says it should have higher energy content, higher thermal stability, it should have lower vapor pressure. So, that is what will be reducing the losses at higher altitude. It says it must have higher specific heat to provide the effective absorption for the high speed aircraft. So, there are a lot of requirements for this kind of fuel what we will be using for our aircraft. It says my fuel system requirement, it should be having say pumping ability, means it will remain in a liquid phase and it will be free from say atomizer. It should be free from the filter clogging by ice or the wax crystal. It should be free from say vapor locking, high lubricity for minimum pumping wear. These all are the properties that is what is required by the fuel system. At the same time, here if we look at, it says like for combustion chamber, it says it should be free from the contaminant that causes the blockage of small passage, because we are using say fuel injector, fuel nozzle which are having smaller dimension, because we need to do atomization. Let me put it the point here. It should be making your atomizer, your fuel injector should make this droplet as tiny as possible, then only it will be giving the good atomization. It should get vaporized rapidly. At the same time, it should not make the carbon formation, otherwise it will be acting like a clogging to my flow. Less carbon content, that is what is to avoid the carbon deposit as we discussed. It should be relatively small amount of S, that is what need to be coming out, because this S particle that will be striking on our next component, that is turbine, and those turbines they are having the cooling mechanism. It may be possible this S particle that will block the cooling holes for the turbine, and that will give the catastrophic failure. It should be free from the alkaline metals, and it should be in freedom from say vanadium. So, these all are the special requirements. So, let us look at what all are the aviation fuels which are available for the aircraft. It says we are having JP1, JP4, JP5 and Jet A fuel. So, here if you look at, it is dedicatedly been written. It says JP1, that is what is my aviation fuel, most widely been used. If we are talking about JP4 or Jet B, that has application for the military purpose. It has a special property, that is what is required by the engine. Same way this JP5, it is little safer fuel. For commercial application, we are having Jet A fuel. Here in this case, if we will compare my stoichiometric air fuel ratio, that is what is almost same in this case. But the property, that is what is we need to understand is in terms of my flash point and what is my boiling point. Okay. At the same time, there is not much variation in terms of heating value. Okay. So, this all are the properties, that is what is demanded by the aircraft and demand for my combustion chamber. So, here in overall if we look at, we started discussing about say combustion chamber, what all are the need, then how my combustor, that is what is working with. Then we were discussing about say what is the construction detail of this combustors. Then we have taken the approach using control volume and we tried to analyze the thing. Later on we realize we will be having say efficiency term, that is what will be coming into the picture. At the same time, my ideal condition and actual condition, that is what is different because of drop of pressure, that is what is happening inside my combustor. Then we have discussed about what all are the properties required by the aviation fuel and what all are the fuels we are using. Let me put the excuse here, since this course is not for the combustion or say any design of the combustion chamber. So, we will not be going into more detail. This information what all we are discussing at this moment, it is more than sufficient for our course for aero engine gas turbine cycles. So, here we are stopping with. Now, in next session we will be discussing our next component, that is what is turbine, that is what is power generating device. So, thank you very much for your kind attention. Here we are stopping with the session. If you are looking for more understanding of the combustion chamber, if you want to read more material, there are books available by say different authors. I have defined, I have given you the reference material, text material. You can go through that if you are really interested in learning about the combustion chamber and how these all components are working with. Thank you very much for your kind attention.